Let's consider our first example for calculation of capacitance, and it's a very common geometry known as parallel plate capacitor. So what we have is two planes of conductors or two plates with cross-sectional area A. So if you call this to be the length and this to be the width, this would simply be LW. You have another conductor which is exactly like the top one. And the region between these two conductors is filled with a dielectric. So this is a dielectric of epsilon. And we want to calculate the capacitance for this device. So henceforth, whenever I draw a parallel plate capacitor, I would just draw the cross section. So in the cross section, we have a shape which would look like this. This is coming in and out of the screen for a total cross-sectional area of A. And let's say the separation between the two conductors from the inside edges is D. If we release charge Q on the top, so let's say this is what we call conductor 1, this is what we call conductor 2. We release charge Q on the top conductor. If we are 100% accurate, then there would be more charge which would collect on the edges and less charge in the center. You saw this for the disk in your midterm exam too, that charge cannot be uniformly distributed on a disk. So you would get a more charge slightly on the edges and less charge on the center, and the charge would sit on the inside. Why? Because associated with the charge on the top, you also have negative charges sitting on the bottom, and they are attracted to each other. If we look at how the electric field is going to be created, electric field inside is going to be slightly complex. There are fields which are going to come out of the plates, and these fields are known as fringe fields. And there is going to be some curvature to these electric fields. It's not going to be necessarily uniform because the charge is not uniform. This is the most accurate picture. However, for this course, we are going to make an approximation, and the approximation we are making is that area A is much larger than the separation between those two plates. And this is a decent enough approximation even when we go to integrated circuits. The ratio between A and D would typically be of the order of a 10 or so. We are going to work under this approximation. The results we have would violate some physical laws, but it would give us an approximate answer to what the capacitance would be for a parallel plate. Let's set it up. Under the condition that area A is much larger than D, we are going to approximate that charge Q and minus Q are uniformly distributed. On conductor 1 and 2 respectively. So we have this conductor. The approximation effectively we're making is that the charge is uniformly distributed. It would sit on this inner side of the conductor on the top and the upper part on the bottom. So you have a negative charge which is present here. Since you have released a charge Q, the charge density Q would simply be Q by A. And you have released charge minus Q here, the charge density would be, let's say, rho 1 and rho 2. This would be minus Q by A. This is what I'm assuming to be conductor 1, and this is what I'm assuming to be conductor 2. And in the middle, we have a dielectric of epsilon. Now, either you can use the conductor boundary condition we had learned before, or you can go and make a Gaussian surface to try to calculate the electric field. And since because it is a nice linear system, we can use our Cartesian coordinates. Let's say this is x direction, this is y. Let's call this y is equal to 0. This point would be y is equal to d. So we go to some point y above, and there, to calculate what the electric field looks like, what would the electric field here be, we made this Gaussian surface. And on that Gaussian surface, we can now apply our Gauss law is equal to Q. And again, remember, D inside the conductor is 0. We don't have to worry about the flux on this face. The flux would only exist on the bottom face over here. If this face has an area A1, we can write it as dA1 is equal to rho 1 A1, or D is equal to rho 1, simply Q by A. Once we know the value of D, E is very simple to calculate there. E is simply D related by the epsilon at that point, and the material we have is epsilon. So this just becomes a D by epsilon, or Q A epsilon. And by inspection, we know D should be pointing from plus to minus, and in our coordinate system, by inspection, E should be pointing in minus y direction. So that allows me to calculate the E very, very quickly. Now what I have to do is calculate the potential difference, and I want to calculate the potential difference del V 2 to 1. So I want to go from conductor 2 to a point on conductor 1, and obviously here E is coming nice and straight down, so we can take a nice straight path up. I have my dl, a small section dy in y hat direction. So del v2 becomes minus integral of E dot dl, which I want to do from 2 to 1, and we get minus E y hat dot dy y hat, which is simply E dy as I go from y is equal to 0 to y is equal to d. Please keep this in mind. What is E? E is a constant everywhere. So E is nothing but a constant. So this simply becomes E times D. For parallel plate capacitors, please keep this in mind. And this is a decent result which we can use many times. For parallel plate capacitors, if epsilon is not changing in space, then E is a constant and del V simply becomes E times the distance, which makes our life we can quickly calculate things without having to set that integral up. If E is a constant, if E is a constant, then the potential difference is simply E times D. It's a result to remember because it will make some of our calculations very quick. All right, let's go now and check, calculate the capacitance. We had said E was Q by A epsilon. And if you want to put the vector, this was minus y hat. And delta V 2 to 1 we had found out to be equal to the magnitude of E times D. Magnitude of E is simply this. So this becomes QD by A epsilon. After that, capacitance is pretty straightforward to calculate. It would be simply Q delta V 2 to 1, and things cancel out. You get A epsilon by D. So the capacitance of a parallel plate capacitance would be this. Area, cross-sectional area of the plates, distance between the plates, epsilon, the dielectric permittivity of the material between the plates. What material you placed between the plates. Notice something, that the capacitance increases as you increase the value of epsilon. If I had only air inside, the capacitance would have been A epsilon naught by D. If I put a material where epsilon is epsilon naught epsilon r, then capacitance becomes A epsilon naught epsilon r d. If I call this air, this becomes epsilon r C air. The capacitance increases by the same relative permittivity ratio of the relative permittivity when I put that dielectric material in. We will see later that the energy being stored in a capacitor depends upon capacitance. We want the capacitance to be as high as possible. So for practical purposes, most of the capacitors would have a high dielectric permittivity material between the plates. Most practical capacitors would have a higher epsilon r. And this is not only true for parallel plate capacitors, this would be true for other geometries we will consider later on. Let me also emphasize that this is an approximate result. Let's see what have we assumed. We have assumed that the charge is uniformly distributed on the top and the bottom conductors. And because the charge is uniformly distributed, the electric field is uniform. Everywhere in space. But we have a broken couple of laws here, or one law which we have seen in two different ways. Look, if I go and make a loop on this path, 1, 2, 3, 4. What would happen if I go on this and I have a delta V 1 to 1? When I walk on that path, 1 to 2 I do not do any work. However, 2 to 3 I'm walking in parallel to the electric field. So let's say this was length L. I would have minus EL potential difference here. 3 to 4 I have no potential difference. 4 to 1 we have said outside electric field is 0. 4 to 1 it's 0 too. So if I walk across this path from 1 start, go on a rectangle, come back to 1, I have reached a different potential. Obviously this is not true. We have violated it. And related to this is your boundary condition. We have said electric field here, there is a dielectric material. Electric field here exists. Electric field outside is 0. But across a boundary, electric field has to be equal. So when we neglected the fringe fields, we do violate boundary conditions. The answer we have achieved is an approximate answer. What we are basically saying is that these plates are quite large, at least compared to the distance between them. Yes, there are going to be some fringe fields which are created here, but because these plates are large enough, we are saying forget about these fringe fields. The effect of these fringe fields is negligible compared to the field which is present in a larger area over there. That's the approximation we have made. Another warning I would like to give, some of you have done a parallel plate capacitors in your high schools. And somehow out of that, many students come with a thinking that capacitors are only parallel plate. They come out of the high schools thinking this, that there is only one geometry present in the world, and that geometry is a parallel plate, and the capacitors are only parallel plates. Please do not think that. Any arbitrary shape of two conductors with a dielectric in the middle would act like a capacitor. And in fact, parallel plate geometry has large fringe fields. If you want to use capacitors to store energy, we will later see the energy is stored in electric fields, and we don't want this electric field or energy to leak out of our geometry. Thus, especially for high energy applications, parallel plates are hardly ever used because of this large fringe fields which are present. Go to your AC units in your house, air conditioning units in your house, and there is a large capacitor in an AC unit. Go and look at that capacitor, and you will see a very specific geometry. Alright, that is the parallel plate capacitor, a simple introduction into calculation of capacitances.